Okay, Spartan fans, this video is going to be the second for 3.3 rules of differentiation. So in the last video, we looked at the power rule. Okay, so we're going to look at the product rule and the quotient rule. And there's a bunch of rules of differentiation, and they're all, of course, listed in your book. I'm not going to go through every single one of them. I think some are easier than others. D dx, and you have some function. This means the derivative of this function with respect to x. So essentially, I'm deriving with the x variables. It's not always going to be x. Sometimes it's going to be y, but for now, that's what it means. So if you have something like d dx of some function u and plus or minus v. So essentially that's a sum or a difference. Be careful because u's and v's can very easily be misconstrued for each other if you're not careful with your handwriting. And u's and v's are the primary letters that are going to be used when we derive more complex functions. So just keep that in mind. This means the derivative of the function u with respect to x plus or minus the derivative of the function with respect to x of v. This looks like, oh my God, sum and difference, but you've done this already. You've definitely done this. So if I gave you some function, the f of x, let's say is, how about x squared plus 2x? This is a sum. So this says, find the derivative of the function with respect to x of x squared plus find the derivative of the function with respect to x of 2x. We did this, whatever, last week. Power rule, the derivative is 2x. Power rule, the derivative is 2. And that is the answer. Do you need to show all this? No. I'm purely just writing it out so that you can see it is actually a separate rule. We're going to look at the product rule, multiplication, and the quotient rule. And of course, do some examples of each. So the product rule says that you have some function uv, and you want to derive it. uv, that's a product. And this is, ready? U times the derivative of v plus v times the derivative of x, of the derivative of u with respect to x. This is the product rule. The first function times the derivative of the second plus the second function times the derivative of the first. Okay, I'm going to give you the quotient rule, and then we're going to do one problem using two options, product or quotient. You can write a product as a division, and you can write a division problem as a product. Trust me, I'll show you. We have the quotient rule, which frankly, I don't like it because order matters in the quotient rule. When you add, it's like, okay, whatever, a plus b, b plus a. Quotient rule is slightly different. The derivative of a function u over v, that's a quotient with respect to x. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. I promise you that with use, you'll just know these. You know how to factor much better now because you just get so much practice with it. The same thing is true with derivatives. So I'm going to do one problem and we're going to use both quotient and product. Okay, so let's say you are given y equals x squared plus 5x minus 1 all over x squared. Okay, and I want you to find the derivative. I want you to find dy dx. Also known as y prime. Okay, we're going to analyze u and v and du and dv separately. You may not want to, but trust me, until you get really good at it. So u is my numerator, x squared plus 5x plus 1. The derivative of u with respect to x, power rule, is 2x plus 5. Hey, and if you don't like 2x plus 5, you feel free to find the f of x plus h minus the f of x all over h. You feel free to do it that way. I'm not gonna. V is the denominator. dv dx, power rule is 2x. Don't you love the power rule? Oh my gosh. And now I'm going to plug in. And I'm going to be really careful with my signs. Quotient rule says v. V is x squared times the derivative of u, and the derivative of u is 2x plus 5 minus u, x squared plus 5x plus 1 plus 1. Okay, so I wrote minus here and I wrote plus here. I don't think that affects anything else. No. Okay. So x squared plus 5x minus 1 is my u times the derivative of v, which is 2x. I like to put that monomial in the front, all over v, which is x squared squared. Okay, figure it out. Negative 5x plus 2 over x cubed. That's the quotient rule. I'm going to do the same problem and I'm going to use the product rule instead. So I'm just going to rewrite this and we're going to do the product rule. So if I want to do this problem as a product rule, this is x squared plus 5x minus 1 times x to the negative 2. U is going to be x squared plus 5x minus 1. Du is 2x plus 5. V is x to the negative 2. dv is negative 2x to the negative 3. Okay. So the derivative of y with respect to x is u times dv dx. So this is the, here's product rule. So it's going to be u, which is x squared plus 5x minus 1 times the derivative of v, which is negative 2x to the negative 3. Nope. Plus v which is x to the negative 2 times u. Times du. This should be v and then du, which is 2x plus 5. U times the derivative of v plus v times the derivative of u. All right, and now it's a lot of simplification. That's going to be negative 2x to the negative 1 minus 10x to the negative 2 plus 2x to the negative 3 plus 2x to the negative 2. No, 2x to the negative 1. Goodness for whiteout. Plus 5x to the negative 2. Just distributed. All right, go for it. Same answer. You can choose which property you like to use. This one, I'll admit, is kind of gross by the product property because of all these negative exponents. But you do indeed get the same answer either way. Let's look at an example where you're given the derivatives and you have to work backwards. Given that the f of x is differentiable, which also means it's continuous. If you're differentiable, you're continuous, not necessarily the other way around. You have some function and it's differentiable at x equals 2. You are given that the u of 2 is 3. The u prime of 2 is negative 4. The v of 2 is 1. And the v prime of 2 is 2. Okay. Let's evaluate the derivative of uv. I recommend until you get good at it. This is u times the derivative of v with respect to x. You'll get good at it, I promise. Plus v of the derivative of u with respect to x. U times the derivative of v plus v times the derivative of u. Well, guess what? You know u. U is 3. The derivative, and then the derivative of v is 2. V, which is 1, times the derivative of u, which is negative 4, which I believe is 2. About the derivative with respect to x of, let's do v over u. The previous examples have been u over v. Okay, so we have the numerator and denominator switched. So this is going to be the denominator times the derivative of the numerator. I'm going to write that instead, a little bit cleaner. Minus the numerator times the derivative of the denominator all over the denominator squared. The quotient property says denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. Oh my God, say that 10 times fast. Okay, so u is 3. The derivative of v is 2. minus the value of v is 1. The derivative is -4. All over u squared 9. 6 plus 10, 6 plus 4 is 10, 10 ninths. Okay, let's look at one more. Let's find the derivative. 3u minus 2v plus 2uv. Okay, so this is that whole sum difference thing was the first property I showed you. So this is going to be the derivative with respect to x of 3u minus the derivative with respect to x of 2v plus the derivative with respect to x of 2uv. Yeah, that first example, it was like, well, who cares? We didn't need to separate it, but an example like this one, you definitely do. Okay. There's a constant property, the derivative with respect of some constant times u. It's the constant times the derivative of u. So think of it as like you're pulling this c out in front. C is a constant. So in this case, I'm going to bring the 3 in front. So this is 3 times the derivative of u. So I'm going to write this as u prime. That's the same thing. Writing d dx of u is the same thing as u prime. Minus 2 times the derivative of v. Plus 2. And this one I'm going to write out because writing uv prime isn't really very pretty, so to speak, because then it looks, is this to the first power? Like, what is that? So I'm going to write this as d dx of uv. Well, thank goodness for us, we already did that. We already did u times v right here, and we already know that's 2. 3, u prime is -4. Minus 2, v prime is 2. Way too many 2's in these problems. Plus 2 times uv, which is, guess what? 2. Swear to God, it's like the only number we know how to use. That's -12 minus 4 is -16 plus 4 is -12. Okay, so one of the good things about the video is that, you can always go back and check your work, slow it down, speed it up, whatever, if necessary. Let's look at a short proof. How about, let's prove, oh, sorry, just kidding. That the derivative with respect to x of -u is equal to negative du dx. Okay, so we want to prove this is true. So essentially, we want to show that when you have a constant multiplied by the function, it's the same thing as the derivative, the negative derivative. So the derivative of a negative function is the same thing as the opposite of that derivative. Okay. So let's start by u equals the u of x. This is just a function of x. That's all that is. It's just a function. Okay, so let's plug into our limit equation. So the limit as h approaches 0 of the f of x plus h. So there's going to be the u, actually it's negative u of x plus h, negative, minus the f of x, which is the u of x, should be minus the negative u of x. There we go. It's negative u of x all over h. The negative u. So the f of that is negative u of the x plus h minus the f of x, which is the negative u of x all over h. That is a lot of x's and a lot of negatives, etc. So this is the limit as h approaches 0. These are both subtraction, wouldn't you agree? So this is negative u of x plus h minus the u of x all over h. So essentially, this negative here and then negative. Sometimes we get confused with our negative signs. If I were to distribute this, this would be plus the u of x. So if I were to not distribute, but well, think of it as a -1. If I were to subtract the whole quantity, this would be plus u of x. Okay, well, isn't this the opposite of the u of x? So the constant. This is a little bit of circular reasoning. And this, of course, is negative du dx. Lucky for you, not a whole lot of proofs. So you're probably going to want to go back and pause this and take another look at that. All right, last thing. Let's look at some tangent lines and how, yeah, you could do it the long way, but I don't know why you would want to do that. So let's look at some questions about tangents. Okay. You have the curve y equals x cubed plus x. Anything that deals with the slopes of tangent lines involves the derivative. Anything that involves slopes of tangent lines involves the derivative. So guess what? Derivative of this function with respect to x is 3x squared plus 1. I don't even know what the problem asks me to do, but I'm sure that there are slopes and tangent lines and derivatives involved somehow. So it says find the tangents to the curve where the slope is 4. I should have told you earlier. This is number 28 on page 120. This is the equation. That's the derivative using the power rule. I want to know where the tangents are for. Well, how about we take the slope of our tangent, which is 3x squared plus 1 equals 4. Okay, so 3x squared is 3, x squared is 1, x equals plus or minus 1. Let's find the f of 1 and the f of -1. So the f of 1, I believe, is 2, And the f of -1, I believe, is also 2. Pretty sure. -2. All right, point slip form. Y minus 2 equals 4, x minus 1. Y plus 2 equals 4, x plus 1. It occurs when x are these two values. To figure out the y value, I plugged in. So I use the derivative to take care of the values, the slope. And then I use the function to get the actual value when x was 1. There you go. The last part of the question asks you, where is the slope? At what's the smallest slope? And at what value does the curve have this slope? Okay, so if I graph the derivative, I want to know where is the minimum. If I want the slope to be the smallest, I'm looking at the derivative because that's slope. So I already plugged it into my calculator. And it's a parabola. Remember, this is the graph of the derivative. And the slope is going to be the smallest at the vertex of this parabola. So the vertex of this parabola, actually, you didn't even need your calculator for it now that I think about it. So M is smallest at x equals 0. That's section 3.3.